Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the 12th lecture in foundations in CNN. Now before we start with different backbones, let's quickly go over some of the components that are used in these CNNs, right? And these are all components that we have reviewed in previous lecture. So essentially all the building blocks of these CNNs are essentially something we are familiar with. So we have gone over convolutional layers, pooling layers, fully connected layers, different types of activation functions and the normalization techniques, right? Now this is the normalization operation that we had seen in the previous lecture, where we have an activation map which is highlighted by orange, and after normalization we get a proper normalized image which is with proper mean and standard deviation, right? Essentially we also have observed that the normalization is usually after the linear and convolution layers and before the activation functions. So essentially we would have these convolution layers passed through the normalization functions and essentially then fed into the activation functions, right? Now this is a quick recap into different operations. So we have reviewed, or we know about the convolution operation where we have a given image. Now convolution operation is essentially a systematic way of extracting local information inside the image. For any given image I with a corresponding filter, we can perform the convolution operation, right, which is defined by this equation. We also have seen the use of the convolution operation for a grayscale image. For example, we have an image from MNIST dataset and we pass it through a list of learnable filters which generates the activation maps, right? And we have also gone over pooling operations, right? So pooling operation is essentially to compress a feature map while keeping the most important information, and the intuition is to identify the local feature which has either a mean of different activations or the highest activation in that particular feature map. So if we take max pool, it is essentially identifying the maximum value of the activation within that local receptive field, or else an average pooling which generally just gives us an average. Now the purpose of pooling could be to reduce the dimension, it could be robustness against translation, or it could be to keep the presence of the features, essentially the presence of the features with the highest activation or the mean of all activations, right? Now these are all the fundamental blocks that we have reviewed and we know from previous lectures. So in this particular lecture, let's go into different backbones. So essentially we want to review the different convolutional neural network architectures. Essentially we will go over these fundamental architectures, which is LayNet, AlexNet, VGG, Inception modules, ResNet and even the Google LayNet. Essentially these backbones were developed in the main purpose was to address this particular challenge, which is the large scale visual recognition challenge, which was hosted till 2017, and it essentially focused on this dataset which is an ImageNet dataset. So essentially you have 1000 classes, the task is a classification task, and the goal is it is open to the whole community who can develop a strong backbone to get the lowest possible error in the validation in the test set of that particular dataset, which is ImageNet. Okay. Now essentially through the development of various CNN backbones, what was observed is that these backbones or the sophisticated variants of these backbones essentially learn fundamental features which are useful for the semantic interpretation. So in the sense that if we have features about, let's say, a person, right, and we have the features which are essentially not going to change when the person keeps changing, like the low level and the semantic information would more or less be consistent, right? And since the backbones learn this kind of an information for classification task, they could also be used for other downstream tasks, right? And hence these backbone has become quite crucial when we are doing development of other downstream tasks. This is something that we will discuss in maybe the subsequent lectures. Now the goal of this particular lecture is to go over the basic understanding of these backbones and to appreciate or to understand, is there a very specific problem that they solved, and then to ask the question that is so let us say that, like, is the best way to develop a backbone just to develop a much more deeper and wider model, right. So if I wanted to beat state of the art, should I just build a very deep model with a lot of learnable parameters? Does that do the job? So that is something that we will try to see over while we are reviewing these backbones. Also, one note is we will give a very brief summary of these models, and essentially what we would expect is that from the relevant citations, please read those papers in detail, right. Try to see if you are comfortable reading the papers. Do you find any difficulty when you are going through certain terms, right, and essentially you should be more comfortable reading the papers and getting a very strong interpretation from the technical part of the paper, right, not the motivation or introduction. Like, the paper has been developed, do you understand, is it clear to understand the experimental setup, is it clear to understand the backbones, what are the architectural modifications done, are you comfortable with that reading, and hence it is recommended to read papers for all of these backbones, right. Okay, let us start with the first network architecture, which is essentially LayNet. So LayNet actually consists of convolution layers which has a kernel size of 5 cross 5 with a stride of 1. It also has pooling, which is essentially an average pooling mechanism with a stride of 2, right. Now we observe the network architecture of LayNet in the figure here, right. So we have an input, this is passed through convolution layers, pooling layers, and essentially we have a fully connected layer. Now we can also express the architecture in this particular fashion, which is convolution followed by pooling operation, then convolution followed by pooling operation, and finally the fully connected layers, right. Now this is a very simple LayNet architecture. However, it was one of the first architectures which was established, and a lot of members in the community started with this architecture itself and then build sophisticated versions from this particular architecture. Now let us take a look at the challenge. Let us take a look at this particular challenge winners over various years, right. Now in the first early, let us say early 2010s till 2012, we had very traditional machine learning algorithms or else shallow models. Now in the middle, okay, from 2013 to 2014, essentially there were the rise of CNNs, and there was using different type of visualization and different type of tools. We saw sophisticated algorithms, and finally with the with ResNet, the very deep network architecture were established, right, and hence ResNet does solve certain fundamental challenges, which is why from 22 layered CNNs it was able to go till 152, and as we observe, the rest of the challenges also worked on very deep networks, right. So let us discuss these models in a quick overview and try to see what problems they try to solve. Let us start with the first CNN winner, which is the AlexNet. Now AlexNet essentially has 5 convolutional layers and the remaining fully connected layers. The output of the last fully connected layer is fed to a 1000 way softmax, since it has 1000 classes. Now the last fully connected layers would also have 1000 neurons, since there are 1000 classes, right. Now this is the network architecture from the paper itself, and we can see that it has an input image which is passed through different layers, right, and these layers could have convolutional layers followed by max pooling layers, right, and so on. Now let us also look at the architecture the way we had denoted it last time. So the architecture could be identified as convolutional 1, max pool, norm, followed by convolution layer 2. So we have first layer, second layer, third layer, and then 3 fully connected layers, right. So this is also one way to represent the architecture. Now let us look at 2 two fundamental parts here, right? Like two operations that are required. Now on the right we have the image, which is the network architecture, right? It takes an input image, it passes on through these blocks. So we have convolution blocks, conv2 blocks, conv3, conv4, conv5 and so on, right? Now the input image has a dimension of 227 cross 227 cross 3, which essentially means it has 227 height, 227 width cross the number of channels. Since it is RGB, the number of channels here are 3. So these are certain elementary things that we will just clear it up now. Now let us actually try to calculate the convolutional operation or the output size after the convolution operation, right. So we can see here that once it has passed through convolutional layer 1, which is conv1, the input, the resolution of the feature map changes. So it goes from 227 cross 227 to 55 cross 55, right. Now essentially if we use this particular formula, which is W dash is W minus F plus 2P divided by S plus 1. Essentially in this formula, W denotes the input dimension, F denotes the kernel size, P denotes the padding and S denotes the stride. Now if we do this particular operation for the output of conv1, right, the input size is 227 cross 227 cross 3. The convolutional operation essentially has 96 as an output channel with 11 cross 11 kernel size with a stride of 4. Now if we have been given this information, then can we calculate the output size of the convolutional layer? Hence the output size is 227 minus 11 by 4 plus 1, which is essentially 55, right. So the output size of conv1 is represented as 55 cross 55. Now the 96 is essentially the output channel, and this output channel is something that the user specifies, right. So now we can essentially calculate the output of any particular convolutional layer if we know the kernel size, the stride, the padding and the output channel. Essentially output channel is just as the last channel. However, we can try to get the resolution of the feature maps. Okay. So if we look at this figure on the right, we can see that the output of all convolutional layers could be used to identify the output size of each of these convolutional layers. Output size of each of the feature maps, which are the output of these convolutional layers. Now let us look at the number of learnable parameters. For convolutional layers, it is highlighted by this particular formula. So it is the multiplication of the filter height, of the filter width, of the input channels plus 1 into the number of output channels, and essentially plus 1 is because of the bias term, right. Now let us calculate the total number of learnable parameters. Now we actually have calculated the output size of the feature map after passing through convolutional 1 operator, right. So after passing convolutional 1, we know the feature map's output size. Now let us look at the number of learnable parameters. Using the previous formula, the number of learnable parameters are given as 11 times 11 times 3 plus 1 times 96, which is the output channel, right, which is equal to 35,000. Now for the max pool layer, which is the layer just after the conv1 layer, the output dimension, the same formula could be used. If we use the same formula, the output dimension is given as 55 minus 3 divided by 2 plus 1, which is 27. Now the output size of the max pool operation is given as 27 cross 96, right. Now what are the total number of learnable parameters in any pooling operation? It is 0. The number of learnable parameters for any pooling operation, whether max pooling or average pooling, is 0, right. Now if we look at the architecture here on the right, we can see that after each convolution we can see the input resolution, right. Now as long as you know the output channel size of the feature map after the convolution and max pool operation, we can actually calculate the resolution of each feature map, right, using the formulas given, and for each layers we can actually calculate the number of learnable parameters, right, for each of these layers. For some of the layers it would be 0, for some of the layers it would be 35k, and we can compute it for each of the layers, right. And hence if we look at any architecture, we can now find out the actual dimension of each feature map after each layer in the network, and we can also calculate the number of learnable parameters in the whole network architecture, right. Some additional details about AlexNet are: it was the first architecture to use ReLU, it used a heavy data augmentation, and it used dropout. Finally, it used learning rate in a manner that the learning rate reduced manually by 10 when the validation accuracy plateaus. Data augmentation is something that we will go in detail in the next class. Okay. Now some of the limitations of AlexNet are observed in the feature maps that we can see on the right. Now we can see that the feature map, which is the A, is the feature map of the first layer, right, and the second one is the visualization of the feature map after the second layer. Now filters in the first layer are not normalized, right. We can see that a lot of filters here are actually dead, in the sense that they do not contribute to any meaningful features, right. Secondly, the mid level features are too simple. Now as compared to other grad camps that you would observe, these values are too simple, mid level features. Now based on this particular observation, ZFnet, which is something that we discussed in the last lecture, actually used its visualization techniques, improved the hyperparameters of AlexNet and got an error. It reduced the error from 16.4 to 11.7. Now we have actually discussed this architecture before. Essentially it builds up upon AlexNet, but they use different visualization techniques to identify the importance of different kernels and different operations throughout the network, right. The major modifications they made after the feature visualization process was, in Con 1 they changed the convolution with an 11 cross 11 with stride 4 kernel to a 7 cross 7 kernel size with a stride 2, and for the other layers, which is layer 3, 4, 5, instead of using these as the filters, which is 384, 384, 256 filters, they used 512, 1024, 512 filters, right. Essentially they increase the number of filters, which is they increase the number of depth of the channels after each of these convolutional layers, right. This resulted in the drop of the error in the ImageNet challenge from 16.4 to 11.7, right. Now these are some of the observations that ZFnet made, which is some of the observations we have seen earlier as well. So the B figure actually highlights the figures from the layers. The B figure highlights the first layer features from AlexNet, and corresponding to that we can see that the C figure highlights the same features in ZFnet, right. And similarly the D visualizations highlight the second layer features from AlexNet, and the same is observed in E for ZFnet. Now as observed in this figure, the representations in C compared to representations in B look more fuller, look more meaningful, and this is similar to what we observe in E compared to D, right. These are visualizations, however they do seem to have retained more information in certain parts of the feature maps for certain parts of the objects, right. So ZFnet, the visualizations of first and second features does highlight that there are certain features that are learned better in ZFnet, which results in a lower error. Okay. Now, since we have discussed AlexNet and ZFnet, let us look at the architectures which essentially led to the rise of CNNs, which is VGG and Google LANet, right. So, let us start with the VGG architecture. The VGG architecture focused more on small filters and deeper networks, right. Some of the variants of VGG are VGG 16 and 19. Now, essentially the VGG models focused on two concepts, which is using convolution only with 3x3 kernel size and stride 1 padding 1, but the focus is on the kernel size, which is 3x3, and similarly to only use a 2x2 max pool, essentially with a stride 2. Now, the network architecture of VGG is something we can observe on the right. Now, similar to what we did even in AlexNet, which had an input image, it was passed through different convolutional layers. The output of the convolutional layers are represented on the right, and we can use the same formula to define or to write the output size of these feature maps, right. Additionally, we can also comment on the total number of learnable parameters in all of these feature maps or all of these layers. So, essentially the number of learnable layers in con1_1, con1_2 and max pool 1. For max pool it would be 0, right. Now, one fundamental concept that VGG actually explored was that it stacked 3x3 convolutional layers and found that it has the same effect as a 7x7 convolutional layer, right. Now, let us take a deeper look into this particular point. Now, in VGG network, essentially the philosophy is to use a stack of 3 convolutional layers. So, if we have an input, we have 3 convolutional layers one after another, right. Now, these layers have the same effective receptive field as one 7x7 convolutional layer. Essentially what we are trying to establish is the blue box is essentially the kernel size from a 7x7 convolutional layer, right. Now, if we have 3 successive convolutional layers of 3x3, then the effective receptive field of this particular conv layer 3 when projected on the input would be 7x7, and this is something that now essentially if we look at the receptive field calculation for kernel size k stride s is equals to 1 and the receptive field RL after L layers, we can represent this receptive field using the formula given. So, after conv1 the receptive field essentially is 3x3. So, we know the receptive field here. For after conv2 the receptive field is 5x5. So, essentially we know the receptive field here, and after conv3 the receptive field would be 7x7, which we know it to be here, right. Essentially the conv3 the projection would be similar to 7x7, which is similar to the receptive field after a 1 7x7 conv layer. Now, essentially the key takeaway from VGG is that using multiple 3x3 convolution layers instead of 7x7 convolution layers captures the same context, but with fewer parameters. This is essentially to reduce the number of parameters, and since they reduce the number of parameters, it did help them for better learning also. Okay. Now, let us look at the learnable parameters, but let us not count the bias for simplicity. The number of learnable parameters, which is conv1, is given as 3 into 3 into 3 into 64, which is 1728. Now, let us look at the learnable parameters in conv1_2, which is written as conv2 here, which is 3 into 3 into 64 into 64, which is 36,864. The number of learnable parameters in max pool is 0, right. So, in the first part we actually know the number of learnable parameters and we can repeat it for all the other steps, and the total the number of learnable parameters in VGG16 model is 138 million parameters. So essentially all the number of learnable parameters in various backbones generally range in this particular ballpark itself. So it can go till 90 million and it could go higher, but generally it is in this ballpark, right, which for VGG it is 138 million parameters. Now let us take a look at the Google LeNet. Google LeNet essentially is a deeper network, and the main objective or the main benefit of using Google LeNet is the computational complexity. Essentially it is 27 times less than VGG16, right, and they propose a newer inception model which we will look into later, right. Now it has improved the utilization of computational resources inside the network, and this utilization or this parameter or this architectural tuning has actually helped to reduce the computational complexity. Now before we start with that, let us look at the vanilla inception network. In vanilla inception network essentially we have a previous layer which is the feature map from the previous layer. We pass it through 1 cross 1 convolution, 3 cross 3 convolution, 5 cross 5 convolution and max pooling, right. Now once we pass through all of these layers, finally we do a feature concatenation, right. What does it mean by feature concatenation? Let us assume that after the output the dimensions of the 1 cross 1 convolution would be height, width and C1, right. Similarly for 3 cross 3 convolution it would be height, width and C2. For 5 cross 5 convolution it would be height, width, C3, and for max convolution let us assume it is height, width, C4. Now whenever we are doing or whenever a concatenation operation is performed, the resolution of all these feature maps should remain the same, right. Now when the feature concatenation is performed, essentially the new feature map would be height, width, C1 plus C2 plus C3 plus C4. So essentially all these feature maps are concatenated. So it is like essentially just putting one feature map below the other, right. Now in the inception architecture the filter sizes were restricted to 1 cross 1, 3 cross 3 and 5 cross 5, and a vanilla version of 5 cross 5 convolution is used. Essentially this led to a much increase in the number of parameters. The pooling operations which are there essentially preserve the channel depth, right. Pooling essentially works on the resolution, not on the channel. Now the idea that essentially Google LeNet proposed into the proposed idea for the inception module used by Google LeNet was to use 1 cross 1 convolution to reduce the channel size, right. So the channel size that we see here essentially they were reduced. The intuition is even low dimensional embeddings contain information about a relatively large patch. So we do not need a very big feature map. We do not essentially need a very big feature map, right, to learn the important information. We could actually have a lower dimensional feature map which could also retain a similar amount of information, right, and hence the proposed inception model is observed here. So we have previous layer, from the previous layer we have 1 cross 1 convolution which is similar to how it was in the vanilla inception module. When I say vanilla inception module, it is the inception module as it is, there was no change. In the proposed one they have made their own changes, right. Now in Google LeNet essentially before the convolution operation a 1 cross 1 convolution was added, and after the max pooling operation also a 1 cross 1 convolution was added. Now essentially the use of 1 cross 1 convolution, which is something that we will see later on, but the 1 cross 1 convolution essentially is the kernel size is 1, right. So this actually preserves the height and width, however it changes the channel depth, right. So essentially the channel depth could be increased or decreased, and in this case it is used to decrease. So the previous layer feeds into the 1 cross 1 convolution, the total number of channels here are decreased, right, and then it is passed to the 3 cross 3 convolution. So in the overall output of the 3×3 convolution, the resolution is maintained, but the overall channel depth is decreased, right. And the main idea that they proposed is we do not need a very high dimensional high channel feature map. We can try to approximate the same information using a similar feature map of similar resolution but lower channels, right. This same operation was done even for 5×1 convolution, right, and additionally after the max pool operation. Now the bottleneck layers use 1×1 convolution to reduce the feature channels. Essentially this reduces the overall depth after feature concatenation. So after feature concatenation at this particular level, the overall channel decreases. This optimizes the local network, which is just one module of inception net. However, since it keeps iterating over throughout the architecture, the overall architecture is more optimized, right. Now if we look at the Google LayNet architecture as observed on the right, again apologies for this architecture, since it is a very huge architecture, it is hard to put it in the figure, but please refer to the original paper and go over the architecture in detail. Now training was done at various scales. Essentially the visual information can be processed at various scales, right, and hence okay. Now one thing which has been done in the Google LayNet is essentially using auxiliary classifier. Now what is the meaning of auxiliary classifier? So the model actually has one classifier, however there are auxiliary classifier or additional supplementary classifiers added, right. Now by adding auxiliary classifier connected to the intermediate inputs, it increases the gradient strength, and at inference time these networks are discarded. So during backpropagation you would have gradient update from this particular, which is the actual output, but you would also have a gradient update throughout these, right, because we will calculate the error. When we calculate the error, this would contribute to the gradient which would flow in the earlier part of the model, right. Now we have actually discussed VGG and Google LayNet, which was essentially they resulted in the rise of CNNs. Now let us take a look at ResNet, which is our last model, which is essentially from the ResNet the philosophy of using very deep networks was established, right. Now ResNet actually works on, or ResNet actually builds on the foundation that deeper models have better representations. However, this statement does not stand on its own, right. What do I mean by that? Now if we observe the curve here, right, which is the training error and the test error, right, and we have two models, right. These are not ResNet models, these are two simple vanilla models, one with a 20 layer and the other is a 56 layer model, right. Now we observe that the deeper network actually has higher training and test error. This is observed in both scenarios, training as well as test error. So although this statement does seem intuitive that deeper models have better representations, however in a vanilla setup this may not always be realized, and this is something that the ResNet tried to focus on, right. Essentially the drawbacks of training a model which is very deep is, first, it is harder to optimize, right. When we say it is harder to optimize, it is not an overfitting problem, it is harder to optimize because of other issues, right. One of those issues is the vanishing gradient problem, and this is something that we had discussed in the chain rule also. When we look at dou L by dou W, it essentially looks at the gradient update, right. It is multiplication of the learning rate, it is multiplication with respect to the local gradient, and it is multiplication of the input xi. Now the local gradient actually depends on the gradient of the deeper layers. In case the deeper layers gradients are not updated properly, or else they are affected by the activation functions, then this value, which is dou L by dou W, would be very low, right. This leads into vanishing gradient problem, and this is something that is very prevalent, or this used to be very prevalent in deeper models, right. Now what ResNet did was it proposed a residual identity mapping within the network. So let's assume that we are focusing on X, which is a feature map, and it would pass through this particular layer, which is, let's assume, a convolutional layer, pass through ReLU, and again the weight layer, which is a convolutional layer. Now an additional skip connection, right, this is skip connection, which is X, is used and added, right, to the main branch itself. Once you add it back to the main branch, you have the output which is given as f of x plus x, right. So essentially we have x, which is the input feature map, we pass it through different weight functions to get f of x, which is essentially an output of convolution layers, etc. However, since there is an identity function, the output after the skip connection is given as f of x plus x, right. Now one point which is a very valid point is that when we are adding it back to the main backbone, right, the feature dimension at the earlier part of the model and after it has been passed through convolutional layers, right, would not be the same, right, it would either be same or smaller, right. And we saw in the concatenation operation, and also this plus also denotes concatenation operation, we saw in the concatenation operation that the height width should be the same and the channel are added, right. So even in this particular scenario, the height width should be the same and only the feature maps are added across the channel, essentially they are stacked. Now to handle this particular approach, handle this particular issue of changing feature size, there are two approaches. In case there is no major change in the feature size, feature dimension, then it is 0 padded with skip connection to increase its dimension. However, if there is a drastic change in the feature dimensions, which is, okay, we need correction here, okay. Lastly, let us take a look at ResNet and take a look at the overall network architecture. Now as observed, the overall architecture is shown in the right. We have an input image, the input image is passed through the convolution layers and across a pooling operation. Once it is passed through this, there is actually convolutional blocks. So there are blocks of 2, this is the first layer, then we have blocks again of 2, which are essentially blocks of 2 in each layer. Now we observe that the skip connection actually connects it in the next block. So in 2 convolutional layers, then a block, 2 convolutional layers, then a block. This is the overall architecture of ResNet, right. So it is a simple backbone that we have been observing earlier, however it has skip connections, right, okay. This is also the various variants of ResNet that exists. We saw earlier that there is a convolutional one layer with 7x7 kernel and we have a max pooling layer. Once these two are, once after these two layers, for different variants, which is from 18 layer variant to 152 variant, it operates in a recursive manner. So let us take the 18 layer variant. We will have 2 convolution layers of 3x3 kernel size depth 64 followed by 3x3 kernel size depth 64. After this there would be a skip connection and this would be repeated 2 times, and this goes on similarly for others, right. So we can take one more example of layer 34. Let us take the first layer. So we will have 2 convolutional layers, convolutional layer 1, convolutional layer 2, right. So this is the first layer which is 3x3 kernel. Now there would be a skip connection after this. This particular thing would be repeated 3 times, right. So this table actually is just for simplification, however we do understand its interpretation and we can draw a corresponding diagram for it, right. Now ResNet variants, there are existing variants and there are lot of variants as we observed in the last table, and this is something that we will observe in the backbones itself, that this follows the mechanism of CBR, convolutional batch norm ReLU, right. This is something which exists, or this is a common framework which is used Again, it's not used everywhere, but in general CBR framework is used, which is just have a convolutional layer, follow it with a normalization layer, follow it with a ReLU layer. Now in ResNet architecture, Xavier initialization was used and no dropout was used. Now when ResNet was released, it essentially took over all these competitions, right? So it was like too good to be true for all competitions. So it was first places in 5 tracks for ImageNet classification, detection, localization, COCO detection, segmentation, and you can see that it has a consistently better performance. Now the main reason for this is because it was able to realize deep networks. However, it was able to realize deep networks and solving fundamental problems in these deep networks, right? Now although the competition has been concluded in 2017, there are newer benchmarks that are released for various tasks, and there are newer architectures and newer modifications, newer learning things which are operating, right? So although the benchmark, that specific benchmark of ImageNet has been closed, there are other benchmarks, and some benchmarks which are related to aerial imagery as well has been released recently, and lot of fundamental changes are still going on, right? Now we have discussed all of these architectures in detail, which is AlexNet, ZFNet, LayNet, VGGNet, GoogleNet and ResNet. There are existing popular backbones also. For example, MobileNet and EfficientNet are essentially to make the model perform better but at a much lesser complexity, right? There are newer variants like ResNet and ConNet. There are transformers backbone, which is not essentially a CNN backbones, but these are popular backbones that we will see, right? Transformer backbones is something we will see, but the other backbones are also there, and it is recommended to read about these backbones also. The best source is the paper, right? Okay. Lastly, let us touch upon transfer learning. Now we have seen in the visualization process also, we have seen in various other discussions also, that for CNNs, let us say for classification tasks, CNNs learn different types of information. For the low level features, it looks at the early and mid layers, and for the deeper layers it is not very intuitive, but it learns high level representations, right? So we look at the visualizations of a deeper layer, and for a human it is not very clear, like we can only justify it in the sense of an edge, but it has high level representations, right? Now this is an overall structure of a very basic backbone for classification task. So we have image, we have corresponding CNN backbone, which is then fed into fully connected layers, and then an output prediction. The CNN could be it could consist of various operations. So it could be convolution, activation, batch normalization, pooling, various operation. Fully connected could be a list of fully connected layers, right? But we are just looking at a schematic, an overview schematic. Finally we have an output prediction. Now we know, for as observed in the earlier lectures, it learns rich representational features, right, about these images, right? And hence let us assume that I have learned, or I have a backbone which is trained on ImageNet, right, or a backbone which is trained on data sets like CIFAR 10 or CIFAR 100, right? These are different data sets. Once we have backbones which are trained on these data sets, it's in practice it is better to take these backbones and then go to the newer data sets rather than doing a fresh initialization, right? So we have fine tuning techniques. Fine tuning techniques means we can essentially freeze the backbone, focus more on fine tuning only the fully connected layers. This is essentially to maybe fine tune the layers, or if the number of classes in the layers, if the number of classes in the data sets are different, then we would want to essentially have a new fully connected layer with the new set of classes, right? We could also freeze the backbone and fine tune multiple fully connected layers, and we could actually fine tune both fully connected and the convolutional backbone layers. Essentially what the motivation is, since the CNNs have learned information with prior data sets, it is better in practice to use CNNs in pre-trained on those data sets and then use it for the task rather than doing a fresh random initialization, right? So just one example on downstream task is, let us assume that we use pre-trained backbones instead of newer backbones, right? Let us look at an example of unit. So in the classical version or in the actual version of UNet, the backbone was the backbone that UNet proposed, right. So it was the backbone which is not a standard backbone, it is a backbone which it had proposed. However, now there are UNet variants with ResNet backbone, UNet variants with efficient net backbones and so on. And when we are using these particular backbones, in practice we use these backbones pre-trained on ImageNet or pre-trained on other data sets. In general it is ImageNet only, right. So this is for a task of segmentation. Now for segmentation, and we will talk about this in detail, essentially it is the encoder part of the image, right. It is the first shallower part of the information, right. Now for fine grained tasks, the information at the later would be very task specific, and that is okay. We are currently focusing only on the encoder level. The same example can also be observed in the image captioning part, where we have an image, we pass it through a CNN backbone and then it is passed to an RNN to do a image captioning task. However, the image backbone in the CNN backbone is also pre-trained, right. So it is not, it is pre-trained on ImageNet and then trained on this particular data set rather than a fresh initialization, right. So just to summarize, this lecture covers various components of CNNs. We did a very brief recap of different convolutional activation, pooling operations and normalization operation. We reviewed various backbones which were part of the ImageNet challenge, like AlexNet, LayNet, Google LayNet, ResNet and etc. We also understood the learning of these backbones, in the sense that these backbones in the shallow layers learn low level information, and as we become more task specific or deeper into the layers, they learn more high level image information. And this concept could be used for transfer learning, in the sense that when we are training on a newer data set, let us say for classification, we would essentially want to use backbone pre-trained on ImageNet and use it on these particular tasks and so on. For other downstream examples that we will look at subsequent lectures, we would always use models or encoders pre-trained on particular data set and then fine tuned for that newer data set or newer task, right. Thank you.